Fewer people come because I put the lectures online. Man, dropping in attendance. Whew. Yeah. 40%. Okay. 45. Okay, so it is time to start. I love this topic. I love talking about quantum mechanics. It's more fun than thermo. I've had a very adult day so far. I've got one meeting and I got a meeting right after this class. So the joys of contemporary work, I guess. Meetings and computers. That's all we're gonna do. At least we're gonna teach everyone every now and again. Does anybody have any questions about anything before we start? I know I didn't get to this part. I'll just go ahead and do this as an example then. I know I have it set up as a chem quiz, but the idea is here that frequency times a wavelength is equal to speed. And here in chemistry we use a weird symbols, use lambda. Lambda is this upside down Y. That's Greek for L, and then nu, it's like this funny looking V thing, and those are both lowercase lambda, lowercase nu. I don't know why we don't use L like they do in physics or F like they do in physics. Probably because it was pioneered in Germany, and for whatever reason they chose Greek. Okay, but what is the wavelength of the frequency is 4.62 times 10 to the 14 inverse seconds, and a nanometer is 1 times 10 to the minus 9 meters. I'll show you this in my calculator. But the idea is that wavelength times frequency is the speed of light, which implies for lambda is speed of light over the frequency, which is 3 times 10 to the 8th meters per second, all over 4.62 times 10 to the 14 inverse seconds. So that's the unit on frequency is in 1 over time is, and a hertz specifically a hertz is 1 over second. So like in the radio, when you have a megahertz, this is a billion 10 to the 9 over seconds. So that means 1 megahertz is a billion wavelengths per second. So lets you know how frequently, and a radio wave is a longer one, so it's going to have a lower frequency. All right, so let me put this in my calculator. 3E8 divided by 4.62 B14. bit smaller. Okay. So this is where you really need to use this EE function, at least on my calculators, EE. Here, using this part here, I just put the speed of light, 3E8, divided by the frequency there, and then multiplying it by, you see that, by a billion. So if you just hit the, at least on my calculator view, just hit an operation, it'll typically pick up the answer. And so multiplying the wavelength by a billion will give you the answer in nanometers. So it's C here. So anybody have any questions on how to do this? So I know I didn't go around with that, but don't worry, we'll have plenty of time to do other calculations that involve lots of big numbers and lots of constants. Okay, so here is the electromagnetic spectrum, and different types of radiation do different things to matter. So I'm going to start at the low end and work our way up. So on the low end here we have radio waves. So radio waves are the longest, at least in this diagram. You can, but they're very long. They're very low energy. So what radio waves do is they change the way the orientation of the magnetic field of nuclei in atoms. So has anyone ever had an MRI before? I've had 2. I'm the only one. Wow. Okay. If you are ever get an MRI, now mind you, the other thing, MRIs, they are extremely safe. You can have all the MRIs you want, and they will pose basically no hazard. I mean, I would say you want to live in an MRI machine because they're small. And like the first one I was in, it was about my nose was about a half a centimeter to the roof of the machine. And I found out that I was claustrophobic. But the other one, it was a little bigger. So if you're in a machine like the MRI machine, what you hear is it sounds like ka-chunk, ka-chunk, bang, bang, ka-chunk, ka-chunk. What it's doing is they're moving magnets. So they have magnets that are around. It's actually superconducting magnets, so it has a very high magnetic field. And you get blasted with radio waves. So what happens is that the magnets align, make your protons in your body align to the magnetic field, at least the nuclei of the protons, and then they get blasted with radio waves, and then they can look at the signal. I think it's more emission of the radio waves. I don't think it's absorption. Yeah, it's the emission of the radio waves. Anyways, here is a picture of an MRI image of my lower back. So if you ever wonder if I'm a robot or not, the answer is no. This is my sacrum here, and if you can see, I have degenerative disc disease between, this is lumbar 5 and S1, and, or maybe this is a sacrum, I don't know. Either, yeah, I think this is the sacrum, this is L5 and L4. Either way, these two discs on my back, at least at the time, were not healthy. And in fact, here they have this is called a protrusion that was sticking in my spinal cord. So it hurts. So if you ever have a really bad back injury, it hurts pretty bad. At least when you have a spinal injury. But so I mean, you can take a look at my insides, right? Not just an X-ray. I mean, an X-ray will tell you where your bones are. They're getting better with X-rays. But there's also, you can use a CT scan. That's also an X-ray scan. But I mean, X-rays are dangerous. So they are ionizing radiation. Radio waves are completely harmless. You can blast anybody with any sorts of radio waves, and it's not going to have really any physiological effect whatsoever. So, but I mean, this is kind of cool. You can see what I look like on the inside just by using a radio wave. Of course, what else do we use radio waves for besides imaging? We use it for communication. communication is typical for radio waves. But the interaction that radio waves have in matter mostly have to deal with the magnetic fields of nuclei. And then I'm going to go into microwaves. So higher energy than radio waves are microwaves. And microwaves we use for cell phones. Also use them for radar. Radar actually uses microwaves, although radar is an acronym. The R in radar is radio. But nowadays we use microwaves. What microwaves do is they make molecules rotate. So if you hit molecules with microwaves, so if this is water, so water will naturally rotate a little bit. You hit them with microwaves, it'll make them rotate faster. And that's what we talked about how a microwave oven works. So you have water molecules, they rotate faster, and then they collide. The rotational energy is transferred into translational energy via molecular collision. So microwaves make things rotate. Infrared, slightly higher energy, makes things vibrate. So this is oxygen, hydrogen, hydrogen. You hit something with infrared light, it'll make the water vibrate. So meaning the atoms along the bonds it can vibrate like this, it can vibrate like this. So it's kind of vibrating all of them. And there's also, with the vibrations, you can have symmetric vibrations like this. You can have asymmetric vibrations like this as well. So different wavelengths will do different things for those molecules. And look at the name, infrared. So less than red, and then ultraviolet, beyond violet. So infrared is lower energy than red in the visible spectrum. But also with infrared, so when you feel heat, like if you go up, it's like a fire and you feel the heat, what you feel is the infrared radiation. So you're feeling that. You can feel that as heat. And what's happening is the infrared light is hitting your body, and then that's causing your molecules to vibrate. Then by molecular collision, well, because they're right next to each other, the temperature goes up. So same idea with the microwave oven, but infrared works off of molecular vibration, and there's more energy in molecular vibration than rotation. So a photon of infrared light is more powerful than a photon of microwave radiation. And I'm using the words light. The olden way of saying light would be visible light. Now in contemporary science, we consider infrared, visible, and ultraviolet to be light. We don't consider microwaves to be light or X-rays to be light. So light is this branch of the electromagnetic spectrum, although all the equations work the same way for any type of radiation. So it all works. Okay, so radio waves change the nuclei's, atomic nuclei's magnetic fields. Microwaves make molecules rotate. Infrared make them vibrate. What does visible light do? Visible light causes electrons to jump up and down in energy levels. So actually infrared light can do that as well, depending on the energy levels. For low energy levels, most light transitions, most electronic transitions are in the visible range, and then ultraviolet causes very large jumps in energy. Also, ultraviolet light starts what's called ionizing radiation. So light, here is visible light. It's said that the visible light is considered between 700 nanometers and 400 nanometers. And red light being the low energy, violet light being the high energy. So most people can see down to about 800 nanometers though. It gets hard to see. So as you go down in the spectrum, it gets harder and harder to see light that's in the infrared. Like I said, most humans can see it. It has to do with our eyes. Our eyes focus infrared light into our retinas. So since our eyes will focus that, we can see the intensity, and something around 800 nanometers, it looks like a really dark brick red for me. Like it's a slightly reddish, but I say brick red. It's like Black, that's the color of red, if that makes sense. But we can't see it very well as humans. But it's also dangerous, so there are certain lasers. So titanium sapphire, TISAF lasers put out 800 nanometers, and so you can align them using your eyes. The thing is, what you do is you crank up the energy when you do that so you can see it, but it's really bright, and you can, if anything gets in your eyes, you'll blind yourself like that because you have a very powerful beam. So it's dangerous in that regards, but it's useful at the same time. But okay, so red light's low energy, and going up low energy up to high energy, and we have the entire spectrum. The Roy G. Biv, if you've heard that before, the red, orange, yellow, green, blue, indigo, violet. And why indigo? It was to have the extra color. We as humans, we really only see 3 colors. And we have 2 types of cells in our eyes, or our light-sensitive cells. We have rods and cones. Rods detect light intensity. Cones detect color. And we have, at least most humans, we have 3 colors that we can see. Some people can see 4. Some people that are colorblind can't see one of these. So, and here is the signal strength for our eyes' response. So here's red. Red peaks around here, like a little bit after, around 700 nanometers, a little bit after, maybe. But we can see a little bit down in the infrared, typically. And then green, we see green the best. Of any light, any color that we see, green is what we see the best. And then blue over here. And actually, our red, we absorb a little bit in the blue. So does anybody know the difference between violet and purple? So violet is light that's 400 nanometers, thereabouts, in wavelength. Purple is red and blue. We as humans cannot tell the difference. We are not spectrometers. We work quickly. Actually, humans, we have a very good sense of sight. Of all the animals, eagles can see better than we can in terms of distinction, right? So they can see things at a finer point than we can. There's manna shrimp that can see they have 11 different color sensitive cells, I think. They can see very vibrant colors. But the difference is between eagles and shrimp and humans, we have the bigger brain. We have the bigger brain, and we have more of our brain focused on vision. We have a big part of our occipital lobe is typically in the back of our brains. That's really, we have the processing power that we can process the images. So we as humans, we're very reliant on our sight. So other animals, for humans, although, blind people do fine, of course, but it's one of the senses to lose. It's a little bit tougher on humans than other animals to lose sight. But back to this green color. Have you ever seen that fluorescent green color? That the light lime green color that's also fluorescent. It is so bright. You're like, I'm sorry, man, I can't hear you. That shirt you're wearing is too loud, kind of thing. That is the color that we see the best. And I also say fluorescent because if you go out in the sun or anything, there's a UV light. There's additional energy from the fluorescence. But surprisingly, not surprisingly, that is also the strongest wavelength of light coming from the sun. So we are tuned to see the color that is the strongest from the sun is the color also that we see the best. That's kind of an interesting fact as well. Also, our sun, although the light coming from the sun is white, we can also say that the sun is a green star. So not a yellow star, it's a green star because that's the maximum of the wavelength coming from the sun. So that's debatable of sorts. Like, what color is the sun? People say it's yellow. I don't think it's yellow. But it looks white. If we were spectrometers, it would be a green star because that's the maximum of the output of the sun, at least in terms of what the photons, which is the peak of the color, is green. So And you might notice some things like if you get up at night and the lights are off, you tend not to see colors. So the world looks much more black and white at nighttime because your cones, the color sensitive cells need more intensity. The rods have a much lower threshold. And also, if you ever go to a black light party, has anyone ever been to a black light party? Those are fun. You have a black light. Black light is ultraviolet light. And if you have something that fluoresces, fluorescence works off of, it's typically 4 stages. The y-axis is just energy. You have an ultraviolet photon that causes a big jump in energy. The electron goes down to this state that's metastable, and then there's a jump here, and then a wavelength of light is released, and then it just otherwise decays down to the ground state. But the state here, the second and third state that I drew, it's called metastable, a little stable, but then it'll release energy. So and it's lower energy than the ultraviolet. We can't see ultraviolet very well, but then the visible light, of course, we can see. So if you're in a black light party, you have all the lights turned down, so you really can't see that many colors. But suddenly that single wavelength of light, colored light, you can see, and it's enough to excite your rods, and then, your cones. And then so it's like, whoa, that's really bright. It really gets us. Oh, and the other thing is, when our brains, the way we interpret colors is the different signal strength of these 3 different types of cones. So like an orange photon here, so our brain would look at like, okay, I have that much signal from red and that much signal from green and very little on blue. I'm going to call this orange. And if we have a little bit more of that, little bit less, I'm going to call that yellow kind of thing. And that's why over here, if you have red and blue and a photon of this much energy, we can't tell the difference because the signal strength is the same to our brains. And one of those like age-old questions, are the colors I see the same as the color that you see? Does my red really look blue to you or vice versa? And like we don't really know. We have no idea. So I mean, this is something that we learn, that our brains learn how to do. But it's kind of cool though. But like I said, we're not spectrometers. When we receive colors, it's a lot of it's just our basic instinct. Is this something that I can eat? Is this something that'll eat me, or is this something to do with reproduction? For manna shrimp, their colors are all about reproduction. So that's part of their reproduction. Is that why? But it's kind of strange that they have such amazing light-sensitive cells, but they don't have the ability to interpret it except outside of a narrow focus. So, okay, and some other basic kind of physics concepts. White light, so like the light coming from these fluorescent lights, is it's all wavelengths. Well, actually for these, typically they're fluorescent. So same idea. So this fluorescence, there's mercury in those tubes. There's mercury vapor. Okay, and by electronic discharge, there's lightning bolts of sorts, electricity going through those tubes, and it excites up the mercury atoms, and then they go down. One of the transitions is ultraviolet, and so that's why they have shielding around it. Actually, is because you can get sunburnt from them. And around that is phosphorus oxide, and the phosphorus oxide fluoresces. So these are fluorescent lights, but there are specific colors coming from these, and we interpret that as white light. We can't tell the difference. But if you have a prism, you can separate these colors out. So what's white light? White light is all colors. Okay, so it's all colors. Also, the fluorescent lights, they give off light that's heavier in the blues and greens and violets. So there is a red transition. It's kind of an orangish red transition. So to our eyes, of course, we interpret it like, oh, I'm hitting all my. Your brain says, okay, oh, I'm getting hit with all the colors. This must be white light. So But true white light is all colors, like light from the sun is white light with a few things absorbed internally within the sun itself and the atmosphere. But if you break white light up, you will get the entire spectrum as such, at least the visible spectrum. And then, okay, so then violet. So violet and beyond violet is ultraviolet. So less than red is infrared. Beyond violet is ultraviolet. Same thing for sound. If you've heard of infrasonic, that means lower than what we can hear. So we have a range of hearing just like we have a range of vision. Infrasonic is too low of a frequency for our ears to hear, but you can feel it. So like pounding has an infrasonic. So like if you ever been around construction and they're banging something, you can it still has a physiological effect, but you can't feel it. You can't hear it. But like I hate that if you're around construction and all you hear is this clunk. Well, you can hear the thunk, but in the ground you can feel the vibrations through. Or sometimes you can feel like an explosion, like fireworks. I mean, there's the boom, but later on you can feel in your chest. You can feel infrasonic outside of your ears. Then there's ultrasonic, really higher pitched, higher frequency that we can't hear, like ultrasonic cleaners, and dog whistles, right? You can blow up a dog whistle, the dogs all howl. You're like, what's the problem? I can't hear it. We lose our hearing typically in the higher frequencies as well. As we age, we lose that. So, but anyways, let's go back to light, ultraviolet. So ultraviolet light begins what's called ionizing radiation. So Celebrity Jeopardy question, what does ionizing radiation do? What does a jumping bean do? Jumps. What does a kicking horse do? What does ionizing radiation do? It ionizes. How do you make ions? So atoms have the same number of electrons and protons. How does one make an atom an ion? Adding or removing electrons. So how does light make an ion? In this case, it removes electrons. So ultraviolet light has enough energy to remove electrons, and where it moves electrons is on the outside, the outer shells of the surface, or valence electrons. So the higher energy electrons, ultraviolet can get. X-rays go for the core, the electrons more in the center. Or it can. X-rays can get the surface as well. But so ultraviolet light, like I said, it's ionizing radiation, and as such, it's harmful. It's harmful to biological creatures and can give you cancer. Ultraviolet light can give you cancer. X-rays can give you cancer. Gamma rays can give you cancer. What cannot give you cancer are microwaves, right over here. So it's kind of gone out of the media. I guess people aren't worried about it anymore. But people were worried about a long time if cell phones cause cancer. There was even a specific tumor that people said, this is a cell phone cancer, because there was a tumor right by people's ears. So microwaves do not cause cancer. So I'm perfectly willing to stake my reputation on that, if you will, that microwaves cannot cause cancer. And the reason for that, which we'll cover later, is something called the photoelectric effect. So it's so electrons are bound to atoms, and well, let's go back to. So in order for cancer to be formed, a cell's DNA has to be altered. There has to be a mutation, and then it has to be a specific type of mutation that will form a cancer cell. So not every mutation will cause cancer. Also, not all radiation, if you get hit with a radiation, oh, I'm going to get cancer. What radiation does, it just damages cells. So it's just damaging on an atomic level. So it rips electrons off, and then those electrons then can charge other things. Then the electron-hungry things can react, and it causes chemical reaction. Bonds break, bonds form, structures get altered, structures get destroyed. Sometimes it's a good thing. Sometimes like, wow, the cell goes, this is much better. I'm glad this happened. I'm going to pass this information on.
Of course, most of the time, it just damages it. Then the cell repairs it, like, oh, well, this damage is repaired. I'm alive. I can do that. All good. Move on. Sometimes it's damaged. It's repaired incorrectly, and then it causes the cell to grow more quickly than the other cells around it, and that's known as cancer. So although radiation can cause cancer, chemicals are far worse. So it's much easier to get cancer from hexavalent chromium than it is X-rays or ultraviolet light. It's just mutagens and carcinogens are just so much stronger acting, at least biologically speaking. And so cell phones that use microwaves, they just cause rotations, and all they do is they heat things up. That's all they do. If you around a cell phone for too long, it might heat you up a little bit. It'll be a nice heater. The batteries themselves are also heaters. I mean, they're about 85% efficient, but still 15% of the energy goes thereabouts into thermal energy. So you get heated by the battery, and you get heated by the microwaves. Let's apply other logic. So let's say that microwaves do cause cancer. Who would be in danger? Anyone who works around an airport, any pilots, because there's tons of radar hitting planes. The people that operate Navy ships that have the scouting planes that shoot all the radar. I forget the name of them. Anyone on a Navy ship, they have the huge radar tower that spins around. They would all be, tons of cancer. I mean, why microwaves? Why not radio waves? I mean, MRI machines, you get blasted with non-ionizing radiation, a huge amount of intensity. So anyone that worked around a radio station, anyone that worked around an MRI machine, those people would have huge risks of cancer and other effects, and they don't. I mean, also the microwave oven, the person that invented it, he was working on a radar station. He had some chocolate in his pockets, and as he was working on it with the radar on, there was enough microwave radiation that melted the chocolate in his pocket. Okay, he didn't get cancer. So I mean, if you're being hit by the same thing that supposedly is cancer causing, it's so strong. Can you imagine if you had your cell phone and it was strong enough that it melted something? There's even a viral video that turned out later was bogus. It was popcorn popping. That was found out later that was staged. I mean, yeah, microwaves are safe. So texting while driving is much more dangerous than the microwaves coming from your cell phone. Okay, let's go about ultraviolet. And ultraviolet tends to have at least the first part of it. For sunscreens, something called UVA, UVB, and UVC. And beyond that, there's something called vacuum ultraviolet. So that's like vacuum ultraviolet's kind of between ultraviolet and X-ray. Why is it called vacuum? Because it exists in space. When it hits the atmosphere absorbs it. So UVA is low energy ultraviolet. And actually, most humans can see a little bit in the ultraviolet. We don't see it very well. I've seen about 380 nanometers. It looks like super light lavender, if I had to give a name. If I describe it, it looks like really light lavender is what 380 looks like to me. Also, some people that had their cataracts removed. So there's a hypothesis that Renoir, Pierre Auguste Renoir, the artist, his paintings changed after he had his cataracts removed. So they think that he started to see in the ultraviolet. And other animals can see in the ultraviolet. So cats can see a little bit, and some insects, so honeybees and that kind of stuff, can see ultraviolet light. And UVA, so at least for humans, if you say what is UVA, UVA is a low energy ultraviolet, and that is the primary cause of wrinkles as people age. So what UVA does is it causes scarring, so it's high energy, and it can scar the lower parts of your skin, the lower dermal layers. And what wrinkles are, I know I have a big one on my forehead. That's just the way I am. My whole family has it, but it's just, wrinkles are just your epidermis, the top layer of your skin, folding over the shape of your lower skin. You can be born with it, like I have here, or you can get it. You can get it by repetitive motion. So you can kind of, like, if you look at an old person's face, you can kind of figure out like that person smiled a lot, or that person had a frowny face a lot. You can see like, oh, there's the smiling wrinkles and there's a frowny wrinkles kind of thing. You can just by repetitive motion you can alter your skin, and also radiation can alter your skin, your lower layers. And so if you see sunscreens that say anti-aging, it means it absorbs UVA, and the sunscreens don't absorb UVA very well, maybe half. So then there's UVB. UVB is middle energy. That causes sunburns. Sunburns, tanning, also causes carcinoma, melanoma, that kind of cancer. And also, UVB is what we use to make vitamin D. So we can make vitamin D ourselves. So humans, we are slightly photosynthetic. We're not like plants. I mean, we don't generate a primary amount of our food via photosynthesis, but we can generate vitamin D via photosynthesis. So specifically ultraviolet B radiation. So, and that's what we use, and we can generate calciferol, which is provitamin D. So what's a provitamin? Vitamin is, we have macronutrients as humans. Our macronutrients, besides water and oxygen, are fats, proteins, and carbohydrates. That's what we need, lots of those for us to run well. We also have micronutrients we call vitamins. And vitamins are organic molecules. Organic means carbon containing. We also have minerals. Minerals are elements that we need in small amounts. Things like, I mean, of course, some we need more than others. We need more sodium and potassium and iron than most, but we also need like a little bit of iodine, a little bit of cobalt, that kind of thing. Those are minerals. So minerals are elements. Vitamins are organic molecules, and there's provitamins. Provitamins are things that we can turn into vitamins. So specifically our liver, very important organ. It changes provitamins into vitamins, and some vitamins can be very toxic at high doses, and vitamin A. Vitamin A is very toxic at a high dose. So, and a very good source of vitamin A is a polar bear's liver. In fact, if you eat a polar bear's liver, you will die from acute toxicity of vitamin A. Beta-carotene is provitamin A. That's the stuff that's in carrots and red bell peppers and that kind of stuff. You can eat all the beta-carotene you want. You can have so much that your fat turns yellow and your skin turns orange, but it will not harm you. And our body can turn that into vitamin A. So, and that's the provitamin. So we make the provitamin for vitamin D with ultraviolet B radiation. So that is a risk factor if you put on sunscreen. But the truth of the matter is, at least here, I mean, most of us have no problem with vitamin D because it doesn't take much. And we also get it in other foods. It's in milk, it's in mushrooms. Mushrooms are a big source of vitamin D. So you can get it dietary. You don't need to make it photosynthetically. You can get it in your diet. What does lack of vitamin D do? It creates a deficiency disease called rickets. Makes your bones very bendy. And I remember one time when I lived on Oahu, I saw someone walking, and there was a female walking on campus, and as she was walking, I could see her femurs were bending. I'm like, oh, that person must have rickets. Like, how does one get rickets though here? Because you got to be in the sun. She was in the sun. I was always wondering. I didn't tap on the shoulder like, do you have rickets, and how did you get it? I didn't do that, of course, but it's rare. It's rare to see that deficiency disease here. Where you more oftenly see it is somewhere like Sweden or Finland or Alaska, where it's dark during long parts of the year. Luckily, vitamin D is it's fat soluble, so we can store it. So not only we can take that vitamin and we can store it in our bodies and then use it slowly. We don't have to. We can hoard it. Other vitamins, which we'll talk about more in 162, we need every day. Vitamin C and vitamin Bs, they're water soluble. We need to have a constant supply of those. And I say deficiency diseases. The thing with vitamins, most of what we know about vitamins are what happens when you don't get them. So is it that we know for vitamin C, for instance, lack of vitamin C causes something called scurvy. So in vitamin C, the common name is ascorbic acid, anti-scurvy acid. You eat this acid and you won't get scurvy. And we found out if you eat 60 milligrams of anti-scurvy acid a day, you will not get scurvy. So some nutritionists think you should have 200 milligrams though instead of 60, but the 100% is 60 milligrams. So, okay, so UVA, UVB. Oh, and like I said, UVB also causes sunburns and skin cancer. But one thing with skin cancer is that most of it happens when you're younger. So if you're going to get skin cancer, most of the exposure happens when you're really young. So going out in the sun now at our age is not likely, I'm using the words not likely to cause cancer. But it can. But most of the cancer is from your younger ages. So UVC, most of it is absorbed by the atmosphere as well. And then vacuum ultraviolet, none of that makes it through from space through the atmosphere of the Earth. So, and of course UVC is dangerous as well. Then we get into X-rays. X-rays, so ultraviolet light goes for electrons on the surface of atoms and or molecules. X-rays go for the more bound electrons in the center of the atoms and or molecules. X-rays can also get surface electrons as well. They can penetrate further in the electron cloud though. And X-rays can also cause skin cancer. So X-rays can cause bone cancer too. Ultraviolet light will not give you bone cancer. It can give you skin cancer. It can, also our eyes. So when ultraviolet light hits our eyes do not focus it to our retinas. It goes straight through. So a lot of ultraviolet light, so if you hit your eyes with a lot of ultraviolet light, it can cause cataracts, which the cloudiness in the front of your eyes. It can also burn your interstitial fluid in your eyes, but it won't get focused to your retina. Whereas infrared lights will be focused to your retina. So in terms of lasers, ultraviolet light lasers are very dangerous because they can blind you very quickly. A UV laser is not as dangerous because it won't damage your retina, but it can damage your cataract, and it can also damage your interstitial fluid, which the fluid in your eyes can regenerate anyways. And cataracts, I mean, I wouldn't want one, but they're treatable. They just rip them out and they give you a fake one, like a contact lens instead. X-rays though can cause skin cancer, and I think one of the reasons why people hate dentists, I hate going to the dentist, and last time I went, they told me I have great oral hygiene and I don't have any cavities, but I was not like, yay, I'm going to the dentist today. I was like, dentist, kind of thing. People didn't like it even further in the past because when they do dental X-rays, the dentist used to put his or her fingers in your mouth and then pull it. Like when they say, like, if you're getting a dental X-ray now, they're like, all right, hold this and clamp down, and I'm gonna go duck behind this wall while I hit the button. Dentists used to hold that, and problem was that dentists would get scaly, ugly-looking skins, especially for these two fingers here. It's like their hands and these two fingers would get really kind of ugly-looking, and it's from the radiation. So X-rays can hurt your skin too, not just your bones. And also, so Glenn Seaborg, one of the people that helped with in part discovered plutonium and many other transuranic elements. Apparently, his hands were kind of ugly from all the radiation, from working with the radiation. Also, the Curies, Marie Curie, Pierre Curie, they discovered radium and other things. They used to carry radium in their pockets, and they would have sores. Like radium. Oh, here, check this stuff out. Radium can glow green. So and they like, oh, check this stuff out. And unbeknownst to everyone else, they had these sores on their legs right here from carrying their radium samples. So radiation's still scary. Okay, so X-rays and gamma rays. Gamma rays are very high energy electromagnetic radiation. These deal with nuclear transitions. So protons and neutrons, so we're talking about electrons soon. We're going to focus much on electrons. Electrons, energy levels here with visible light. The same thing works with gamma rays. Gamma rays are just like the electron, it's just like the energy levels, but with protons and neutrons. And gamma rays, they're very powerful. They are flying right through us right now. Not many of them, but they tend not to have very much a physiological effect. The radiation, of course, ultraviolet and X-rays have much more physiological effect on humans than gamma rays. So different types of radiation have different effects on people. Depends on where they're at as well. So alpha particles, that's radiation that's not electromagnetic radiation. Alpha particles don't hurt you that much outside of your body. I remember someone asked me about, he was cleaning up ordnance at Col Ave. He was like, well, what if there was uranium there? What if they had the simulated nuclear blasts? And like, should I be worried about the uranium? Like, well, as long as you didn't breathe in any dust or you didn't inject yourself with anything, you should be fine, is what I told him. It's because the alpha particles, they tend to get blocked by your skin. If you breathe them in, though, like if radon or something like that, the radiation will bounce around inside of you and it can cause massive damage inside. So different radiation, I know that's different radiation will cause different physiological effects, and also where it is. So like I said, ultraviolet tends to affect your skin. X-rays can affect skin and bones. Gamma rays tend not to affect anything, to be quite honest with you, but with enough intensity they can still be dangerous. And if you ever study nuclear physics, I can tell you, as a former nuclear physics person, it is a lot easier than chemistry. So nuclear physics is much easier than chemistry because when you deal with electrons, the energy levels are really close to each other, and they act like waves, and they all interfere. So they're trying to make sense of the pattern of all the energy levels through all the waves is really hard. Nuclear transition levels are so far apart, they don't interfere with each other, and it's really easy to do calculations. It's really easy to figure out what's going on with gamma rays. So, all right. How are we doing? Anybody have any questions with a brief lecture on the electromagnetic spectrum? But they all do something. And I'm a spectroscopist. So at least I was when I was a student and postdoc. We look at how radiation affects matter, and they all do things. Okay, so let's talk more about wave-like behavior. So when waves are flowing together, they can have constructive interference and or destructive interference. And this is a perfect case scenario. Most of the time, like if you ever taken rocks and thrown them into a puddle or a lake or something like that and seen the waves come, so there's like this interference pattern that happens. It's usually destructive and constructive interference. So constructive interference, if two waves are in phase, they will add to each other. And if waves are out of phase, they will cancel each other out destructively. But of course, it's usually something that happens altogether. Other things, so wave diffraction. So this is particle versus wave behavior. So let's say that we have a rock wall, and there's a hole in the rock wall, and some ocean waves are crashing into that rock wall. What will happen is that the waves will go through this rock wall this way in a diffracted wave pattern. Let's say instead of the rock wall, the hole on it, say that I'm sitting out there and I start shooting a machine gun towards the rock wall. What's going to happen? Well, the bullets are going to be stopped by the rock wall, and the ones in the middle will go fly through. Right, so you can see that there is a clear particle-like behavior and there's a clear wave-like behavior. Why am I saying this? Because electrons and photons can act like particles and waves. And depending on how you look at them, they will act one way or the other, but not like that's the whole dead cat example, the Schrodinger's cat. It's only when I look at it does it act one way or the other. Okay, so we can get light to act like a wave, and this is called the two-slit experiment. And if you have a light source and you have two openings, and you measure the light intensity behind it, what you get is this kind of pattern here, where light goes through and you get intensities in various bands, the biggest being in the middle. And I drew this over with my blue pen to see that you have this big intensity in the middle. Let's pretend instead of light coming through, let's have Rambo with all of the big machine gun here, and he starts shooting lots of bullets at two holes. What you see in this case is you see two humps, like that. You have the bullets go through one hole, and then it goes through the other. So, and what's confusing about electrons, I said the wave-particle duality with electrons, if you have an electron gun, so what's an electron gun? You take a piece of metal, or like a wire of metal, usually tungsten, and you run electricity through it, just like an old school light bulb. And as electricity goes through that, it'll shoot off electrons. That's a phenomenon called thermionic emission. And you can put some plates on it, and you can charge the plates. And in doing so, and when the electrons go off, you can charge them, and then the electron will zoom. They'll fly off with a certain amount of kinetic energy. So you can make electron guns that way. That's how an old school TV works. So that's a cathode ray. That's how you make a cathode ray. A cathode ray TV, that's how you made the cathode rays in TV. You would shoot the electrons and they would bend and they would hit the screen, and then you would have different colors coming from where it hit. So one of three different colors for a color TV, or black and white or white, or no signal for black. So you can make an electron gun, and you can shoot electrons in the same fashion towards two slits. And even more confusing, you can shoot one electron. You can, instead of two electrons, I can shoot a single electron towards two slits, and then I can look at the energy of the electron afterwards, and with a single electron or a bunch of electrons, I will get a pattern just like that. So you can make electrons behave like a wave, and then you can also have a laser sitting here, and when a laser hits an electron, it'll flash. So it'll absorb the energy and then emit it. So you can absorb the energy and emit the energy. And if I had a detector behind here that detected the light coming from that, and I shot electrons, I would see two humps. So that means if I want to have an electron behave like a wave, it'll behave like a wave. If I want to say, oh, if I hit electrons like this, even if it's one electron at this, that means that it's turning into a wave and it's going through both holes at the same time. I want to see that. Shenanigans. I call shenanigans. I want to see that electron in two places at once. So you try and see where its position is, and it's going to stick to one position. In doing so, it will only go through one spot, not the other. So that's one of the hard things with dealing with these. This is the quantum mechanics, not classical mechanics. Okay, so let's go back to light. And this is how Einstein got his Nobel Prize. Einstein did not get his Nobel Prize for relativity. It was too controversial. So Einstein was not popular. Einstein was extremely popular in the United States. He was hated in Europe. People hated Einstein. Einstein's still popular here. We have posters of him, sticking out his tongue and his hair. He's like, oh, who's that fuzzy creature? That's Einstein. Everyone knows what Einstein looks like. The Brits hated him because he said, who is this German that says he knows better than Isaac Newton, our hero? And the Germans didn't like him because he was Jewish. So what did he do? Came to America. We loved him. So anyways, in relativity was too controversial. So he got his Nobel Prize from this, the photoelectric effect of light. So he took a metal surface and he shined light at it, and he noticed that for lower energy wavelengths of light, so I'm going to show it here, red, yellow, these don't do anything. You get to green, suddenly you start getting electrons coming off at a specific kinetic energy. And I'm trying to show this equal spacing as a slow-moving electron. Now with a higher frequency light, more energy, the light comes off with more energy. If you up the intensity of the light, you don't get faster electrons, you just get more of them. So, and the lower energies do absolutely nothing. So you can hit the metal surface with all the light you want below a threshold, nothing will happen. At least as far as ripping off electrons. Only at light with high enough energy can rip off electrons. And the interpretation of this Einstein had was this, that the kinetic energy of the electron is equal to the energy of the photon, and this in part was also debated, how photons exist, and then the binding energy of that electron. So this probably makes a lot of sense. So so look at the other way around. If I shoot a photon at something, and if I add energy to something and something's ripped off, the amount of energy of the light that I put to rip it off is equal to the energy of whatever it is that throws off plus how strongly it's bound. Makes sense? So if I put 1,000 joules at something and something flies off at 300 joules, that tells me, oh, it's being held onto with a force of about 700 joules. So, that's how this is saying. The kinetic energy, the leftover energy of the electron, is equal to the energy of the photon minus how strongly it was bound. And this historically was a couple things. It told us then that photons themselves are quantized. So what do I mean by quantized? So quantum mechanics, quanta means something. So let's take a step back and look at space. So space-time itself, what we exist in, is quantized. So if we have point A and point B, and to get from point A to point B, there's actually little packets of existence of space. There's not forever space between point A and point B. Why is that? Because you can get there. If there was an infinite number of positions, points between A and B, you could never get anywhere because it would take a little bit of time. It takes time to go over space. And if there's infinite space, then there would be no structure of the universe and nothing would ever happen. Has anyone ever heard of Zeno's paradox before? So a few people have. Zeno's paradox is, I'm going to step half a step towards the desk. Half a step, or half the distance, half the distance, half the distance. I'm never going to get there. That's true in continuous mathematics. If there was an infinite number of points between me and the desk, yes, I would never reach the desk. But space-time exists in little packets of existence, and because of that, I'll eventually be right up next to it, and I can touch it that way. At least I'll be in one quanta of space-time, and then the desk will be in one quanta of space-time. So yes, I can touch the desk. So Zeno's paradox doesn't work in a quantum world. So when I say continuous mathematics, so like you probably y equals x squared looks like this, right? That's a parabola. And if I were to look at some part of the graph and I zoom in, I could zoom in as much as I want. So I can say, okay, well, let me zoom in between points, but between 1 and 2. I can go to 1.0001. If I'm going to go small, I'll go 1.000001, right? I can, with continuous mathematics, I can go as small as I want. Problem is that's not the way the universe works. The universe works is in little packets of existence. We call them quanta. And then you have to work off what's called discrete mathematics, where things exist as valued points. So, and humans work the same way, like as far as discrete. Like if you don't have to have discrete mathematics solely into quantum. You use that, at least as far as things like car rentals, right? So if you have 6 friends and you're trying to get a ride somewhere, and your car can hold 5 people, you're like, well, I need 1.2 cars, right? So what does a 0.2 car look like, right? No, you need 2 cars, right, to fit 6 people, or you need a bigger car, right? So we do discrete math. We just don't necessarily understand that we are doing discrete math. So this introduced the quantum world here, photoelectric effect, and that's also why I said cell phones don't cause cancer, because as via the photoelectric effect, you can hit it with all the microwaves you want. You can warm it up, but you're not going to rip electrons off of things. I mean, of course, you can do other things. That doesn't mean microwaves aren't dangerous. I mean, if you hit something with enough microwaves, you can boil their blood, right? I mean, that's dangerous. They have non-lethal weapons of sorts that are microwaves. They make people feel hot, and they're crowd dispersing. Like, okay, we want to get rid of these people. What do? Hit them with a bunch of microwaves. They feel hot, so they all walk away. So it doesn't mean it's not going to hurt, but it's not going to give you cancer. Okay, and well, you're like, so KE is kinetic energy. What is this H nu? So we learned nu is frequency H. H is Planck's constant. And it's 6.626 times 10 to the minus 4 joules times seconds. And the energy of a photon is also equal to the Planck's constant times the frequency. And if you want to put in this equation, the speed of light is wavelength frequency, you can get this equation here. So how we doing today? Anybody have any questions? All right. Nitrogen laser has a wavelength of 337 nanometers and contains 3.83 millijoules of energy. How many photons does it have? The way you do this is I got dinged in my teaching evaluations like this. You have to use common sense. Let me explain what the common sense is. So it's going to be, you need the total energy all over the energy per photon. So what do I mean by that? So same thing works for money. If I have $20, how many $1 ice cream cones can I buy? 20, right? So my principle, same idea. So I have my total amount of money over the cost per item. Tells me the number I can buy. Right? So I mean, it doesn't necessarily work with more than ice cream cones. Right? So if I have $20, how many $5 hamburgers can I buy? I can buy 4, right? Same idea. So with this here, the number of photons, I have the total energy, and I can calculate the energy per photon. This is equals the H nu equals Hc over lambda. And the total energy is given to us, it's right there. Okay. Does that make sense? So, all right, so that means, I can just do this all at once, what the heck. Number of photons. This is going to equal the total energy, 3.83 times 10 to the minus 3 joules over the, that's a joule, over the energy per photon. So we're going to use the Hc over lambda. So, okay. I'm going to put this down here. H is 6.626 times 10 to the minus 34. Oh, geez, if I'm zooming in, I'll make it smaller so you can follow. Joules seconds. C is 3.0 times 10 to the 8 meters per second. And over lambda, how long is it? 337. 337
times 10 to the minus 9 meters. So let me back up. So you see what we're doing here? Oh, I should have used it here. We have a total energy, which is given, and then we have the energy per photon. Energy per photon is this hc over lambda, and h is 6.626 times 10 to the minus 34 joules per second. Speed of light is 3 times 10 to the 8 meters per second. Wavelength of light, the lambda, it's 337 nanometers. Nano is 1 billionth. Questions on how to set this up? Okay, then we start to put in our calculators. Oh, let me talk about units. So joules cancel, this second cancels, and oh, these meters cancel. There we go. So we're left with just a plain old number with no units. And let's see here. 3.83 minus 3. And I'm getting 6.49 times 10 to the 15th. Jeez. It's harder to write, actually, this finer one. You'll get to do the next one, don't worry. You can use calculator. Another trick, since I knew I was dividing by the 337 nanometers, I put it on top. So I did this times this divided by that. So either way. All right, so recap. We're given an energy and the wavelength. We don't know how many photons. So we take the total energy divided by the energy per photon, and total energy is given to us, the millijoules, and then we take that and divide it by the energy per photon, and the energy per photon is the h nu or hc over lambda, and we get 6.5 times 10 to the 15 photons. So you look at this, and a couple things should go through your head. They're like, that's a lot of photons. Then maybe you start thinking about things like a mole, where it's 10 to the 23rd. Like, oh, so just like atoms, they're very tiny and they're very plentiful. So we need big numbers. The other thing is, like, you haven't really didn't talk too much about lasers. You might see lasers, and they'll have these huge powers on them. For instance, in grad school, I had a 2 gigawatt laser. And you're like, wow, I mean, that's like twice the energy output of a Wahoo. We're at 350 or something like megawatts on the island of Maui. So, I mean, you're looking at like, my laser was 7 times as powerful as the island of Maui. How is that possible? Power is energy divided by time. So my laser put out millijoules, but at picoseconds. So in a picosecond, there were millijoules of energy. So, and power is energy divided by time. So that's what power is. So if you ever see someone that says a laser, it's a very powerful laser, and like, okay, don't hit me with it here, like, I didn't feel anything. It's because there's not a lot of energy, but it's just maybe on the surface. Like if you get hit by a laser pulse, it can ablate, it can vaporize the surface. It can hurt. That can hurt. I was curious one time when I put my hand in the path of a laser pulse, and it hurt. But it's just because it did vaporize the area. So, in the laser, it's not like the military lasers that can cut you in half.
All right, so with this in mind, a laser pulse, so the first harmonic of an ND-YAG is 532. So a laser pulse has a wavelength of 532 nanometers, and as a pulse has 4.67 millijoules. How many photons is this in that laser pulse? So how many people think it's A? How many think it's B? I think it's C. Actually, is anybody getting stuck? I'm mostly concerned about, the answer is A, about the calculator. So some of you, the ones of you that aren't playing, are you? Actually, let me go around and make sure that you're putting the right numbers in the calculator. So let me go around and see what you're putting in your calculators. So who didn't get A? I forgot. Did you get A? You did. Did you? Raise your hand. Did you get it? Yeah. Okay. Okay. You got it. Okay. This is a pretty easy calculation. I just want to make sure you're doing it. Yeah, you can. Did you get there?
I didn't know.
Okay, let's see. Do you mind if I watch it over you? Yeah. Because 1 divided by 1 divided by x. This is because 1 divided by something. All right, that's a shut up alarm. You guys are free to go. And everyone over there on the left side, you guys got it, right? Okay. Okay. Sorry, lean over your shoulder there.
No. I didn't even know she was coming. I mean, I knew she said she was coming here, but she always had those. Like, really call you guys, that's why I always wanted to take days. That's crazy. Like, once you don't go to school, like Jenna told me, like, if that.
Once you come back, it's like
Yeah,
you're getting more, yeah.
She told me that.
So you're gonna like constant, like,
Ever
right
since,
after high school.
right after high school, when she took a break and she didn't come back to this year when we started, she was like, she was like more credits.
Yeah, like, I like people who like don't go to
And she
school.
came back here and she was like, all this from high school. Like I was thinking back, like, some of this stuff. She's like, I don't even remember how to do it. So I was
Yeah,
like,
that's why I'm
bruh.
like,
I don't know. She should have just stayed.
that's what I said.
It's not like she can even drop to being part time. Part time only take like what, less than something credit. At least get the solutions. Okay, it's not like everybody's here anyways, but I have to see on each group, Charles comes to school. A lot of people that I wouldn't even exactly, RJ, Robbie, exactly. Like even getting your associates, you can get bumped up higher in your work area. But she could be the first one to prove them all wrong. Like, even just getting an associate's degree, 2 years, it's not even that hard here for liberals. Wait, why accounting? That's crazy.
You know, you just take your liberals. Just like,
Yeah, and then after you take your liberals, then that's when you
then you can like,
exactly. Because you can actually graduate with your liberals,
Yeah, that's
and it
how.
wouldn't matter if you
Yeah.
went on.
And then later on, you can decide to like go to your So I feel bad. I thought that I
Because the way you had it, the way you did it is that you calculated all this out, right, and then you divided by that. But this is this case here, so it's the same thing.
Oh, right.
Well, just like the way you had it, you calculate this and then divide by that, and you should actually multiply. Yep, okay. Just wanted to make sure.
Yeah. Takes
Yeah, but I mean, it's a skill, actually.
Yeah, it is. That's why I like to let Wolfram Alpha do all of my complex
Fair enough.
arithmetic.